All right, good morning, everyone. It's good morning here where we are. I'm Shegun Henry. I want to welcome everyone to MIT's Inotherm International Colloquia on Thermal Innovations. Today we have a very exciting and very interesting topic and panel with distinguished members to discuss um, on aligning policy to decarbonize thermal energy uh, in industry. And so I want to introduce our host for today. It's Dr. Addison Stark. Addison is the Director of Energy Innovation at the Bipartisan um, Center for Policy, and he coordinates the American Innovation Council. Prior to joining the Bipartisan Center, he was a fellow at ARPA-E in the Department of Energy here in the United States. And there he worked on early stage energy technology development and R&D across sectors ranging from renewable energy, green industrial chemistry, and dry cooling for water conservation and power generation. Also advanced sensor systems for agriculture and leveraging advanced manufacturing for the fabrication of energy devices. While he was at ARPA-E, he also served as acting program director for ARPA-E's Energy Water Nexus portfolio, the ARID program. And he's been the author of a number of journal articles and also popular press pieces. Recently put out a paper on decarbonizing industry. And by background, he did his PhD in mechanical engineering at MIT, and also a master's in public policy and mechanical engineering, also at MIT. And his bachelor's was in math and chemistry at the University of Iowa. So with that, I want to ask Addison, go ahead and take it away. We're really, really happy and appreciative that you've decided to host this session for us, and really, really interested to see what this panel has to offer and teach us about policy.
Actually, thank you very much. And also thank you to all the participants who are here today. Thank you to our panelists. I'm going to go ahead and do a quick introduction of the panelists that are with us as well. I won't be able to give as biographical as you did for me, Asha, but I appreciate everyone joining today. We have Colin Cunliffe, who is a senior policy analyst at the ITIF, the Information Technology and Innovation Foundation, a leading think tank in Washington, D.C., where he focuses on broad range of topics on energy innovation and policy, both R&D all the way through deployment policies, pieces he'll be touching on today. We have Zhuan Fan from the Center on Global Energy Policy at Columbia University, where he also has put out some excellent papers recently focused on decarbonizing heavy industry, looking at steel and cement, also looking at thermal decarbonization, topics that are very closely aligned to many of the things we're talking about today. And Blaine Tollison, who is the director or the executive director of the Renewable Thermal Collaborative, which is an organization of it's an industrial organization focused on helping companies that are trying to decarbonize their thermal footprint. And so he's also active here in Washington, D.C. But one of the points that I want to make right now before diving in is the fact that many of the things we're going to talk about today have a global footprint, that innovation policy, deployment policy for decarbonizing the industrial sector is going to need to play out across the globe. So while we're going to draw on many examples from the US and the EU in this discussion, these are things that many people around the world should be thinking about how their country can be engaged in this. So I'm going to go ahead and bring up my slides now to go ahead and help frame up this discussion. And then we'll go through our panelists for about 10 minutes presentation each, and we'll then pivot to an open panel discussion. So be sure to submit your questions down at the bottom in the Q&A box. And thank you to the additional staff who is helping to sort and bring those to me digitally so I can bring your questions to this panel. All right. So here we are. As soon as I can unfreeze, there, excellent. Perfect. And I believe this is up on top. So I want to start with the framing the fact that a little bit of a statement that in order to decarbonize industry, we must decarbonize heat. That this hard to abate sector, as we're going to be talking about, really has a few cross-cutting opportunities for decarbonization. And so what do I mean by this? Well, today, when we look at the broader climate landscape, we do know that the world needs to move to net zero by mid-century in order to meet climate goals. That somewhere in the mid-century range, we need to be able to move from our current trajectory of emissions, global net CO2 emissions, and then quickly start to decarbonize. We have plans, and many of my colleagues here, along with others that work with us in Washington and other areas around the world in other think tanks, focus on thinking about decarbonizing the electricity sector, the transportation sector. But one of the important pieces is the fact that all the sectors not only need to be able to get to net zero, but eventually go to net negative. So that means a broad innovation agenda to be able to develop the technologies we need across all emitting sectors. And today, if you look across where are emissions coming from, you can track them to primary energy consumption. So if you look at this classic Sankey diagram, which I'm assuming every week this has come up during this seminar series, is, you know, things are kind of equally spread across electricity generation for residential, commercial, and industrial use, but also, as you notice, a huge amount of fossil energy between petroleum, natural gas, and coal is used directly in industry. Some of that's used as feedstock to be able to make materials, but the vast majority of it is used to directly produce heat to drive processes. When you drill down a little bit, you can see that in 2010, a full 13.1 gigatons of CO2 and 176 exajoules of primary energy demand were attributed to the industrial sector, which is roughly 25% of energy use and an equivalent amount of CO2 emissions. If you want to think about how we actually try to decarbonize that sector, it becomes harder much more quickly. If you take a more detailed view of this, if you drill down and you look at and actually I hope that my screen is, it looks like my toolbar might be blocking this. I apologize, but this is from a great website called departmentof.energy, where you can actually drill down and look at each of the individual parts of the industrial sector. You'll see that actually to decarbonize the industrial sector means you need to start to address hundreds, if not thousands, of individual processes. So thinking about innovating and developing a new, for example, a new process to smelt nickel might not be completely, you know, it'd be very expensive. And can you port over knowledge you learn from decarbonizing other technologies? We run into the challenge that industry is a collection of very inhomogeneous processes. So how do we find unifying opportunities to start to decarbonize this sector? One opportunity is the fact that, or thing we need to recognize, that some of these industrial emissions are inherent to their process chemistry. So if you look at the production of cement and steel, the materials that build our world around us, each of these both do have process heat associated with them, but they also have direct emissions of CO2 from their process chemistry. This is something that Fon talks about a lot in his work and focuses on how do we think about re-innovating these processes to make them more decarbonized in their process chemistry itself. However, the most ubiquitous source of industrial emissions across all the different processes that we see in industry today is through the generation of heat. whether it be through steam to drive machines or to do process conversions to drive chemistry. You can imagine steam being used for disinfecting or cooking in food processing, or the very high temperatures necessary to process metals, or furnaces to be able to drive other material processes. So it's a burning problem. Nearly 60% of sectoral emissions, industrial sectoral emissions, and more than 20% of global greenhouse gas are directly attributable to industrial heat, which means, okay, this is a huge challenge, but also it's a huge opportunity. You can go after 1/5 of global emissions by thinking about how you decarbonize the heat used in industry. And as we noticed before, most of these are driven by fossil fuels that are directly combusted to drive these industrial processes. But there's not a one-size-fits-all solution. Actually, you look at the distribution of sizes of thermal loads across industry, and you see that the vast majority is below 10 megawatt thermal. So you can think about this as you have a distributed challenge here, that you need to be able to develop modular technologies that can scale down to the small laundry that is in an industrial sector of a small city. And it's not the same as the challenge of decarbonizing electricity, where you're talking about very large 1,000 megawatt loads that you're replacing and decarbonizing. You have a much more distributed challenge. But also it's distributed across temperature scales. In industry, the demand for heat spans from low and mid and high pressure steam that brings you up to about 250 C. But then you have very high temperature demands up in excess of 1,000 Celsius to be able to drive metallurgical processes, chemical processes. And so you have this challenge of we need to be able to develop technologies across scales and temperatures. And so this is the challenge that we need to bridge. And we need to not only develop the technologies, but we need to deploy them. And that's the important question of how we design our policies to be able to drive and address this challenge. The way that we framed things up in our recent paper was focusing on breaking down and thinking about how you leverage existing approaches, and thinking about how do you actually decarbonize this is focusing on zero carbon fuels, zero carbon heat like solar thermal, geothermal, or leveraging the fact that the electric sector is decarbonizing in parallel. So as that decarbonizes, how much of industrial heat can we electrify? And then ultimately thinking about how internally we develop the technologies necessary to both improve the thermal efficiency and also integration with other industrial and buildings in areas. And so this is the agenda as we see it. However, how do we implement that? And so when you turn to the political framework, the innovation framework, the policy framework, we recognize the fact that the innovation life cycle and policy touch points are different along the innovation chain. And so many of you in the audience today are very familiar with this early stage of looking at basic and applied R&D, where many of you do recognize and probably agree with this bullet, that the big challenge here to the researcher in the university is always that there's inadequate funding for your R&D portfolio. However, when we think about how we actually implement the technologies you're continuing to develop and researchers want to be able to bring to the market, many of you know that there's a lot of challenges ahead to be able to bring and deploy your technologies at scale. Two so-called valleys of death. The first, technological valley of death, things that once you first spin it out of the scientific discovery and try and make your first prototype, are you going to be able to do, can you overcome the engineering challenges, the first manufacturing of a prototype? This has traditionally been a gap that has been more and more addressed by the development of policy solutions by creating applied research organizations that are generally federally funded and focused on. This is an area where, often we run into a challenge of the also being able to transition to bringing it to the private sector. So being able to support private sector companies to take on risks in this area, but also later stage challenges. And many of the things that we need to think about is how do we align incentives to be able to demonstrate technologies at scale, to be able to then also try early adoption. There's many challenges in the industrial sector of no R&D budgets, very little willingness to take on risks that could make it so processes are shut down if a new technology does not have the uptime that a traditional natural gas boiler may have had. And so it's very hard to think about how do we design the programs to demonstrate in situ these technologies. So generally, how we look at this framework, and we'll be talking about this more today, is for the early stage, we need to be able to have the federal investment through direct grants and R&D support. However, when we start to think about the later stage adoption and deployment, is being able to align incentives to get the private actors to come and deploy that technology. And this, I think, is going to be a bigger challenge in this area just because of the fact that we have not yet seen comprehensive deployment of decarbonized heat yet. And so it's going to be a learning curve for those involved, and also the number of different companies that are involved in it. So pieces that I would first send people to, obviously, is the fact that, we've dove into the innovation challenges of decarbonizing heat in a recent paper I put out. Obviously, you should turn to Asha Henry's paper that was the subject of the first of these colloquia series a year ago, thinking about the broader innovation challenges. But for those that are interested in thinking about how we actually develop policies to be able to deploy decarbonization in global industry, I'd recommend people take a look at this. So this balances the technology opportunities, but also the policies. And so with that, I'm going to go ahead and turn to my colleague, Colin Cunliffe. I'm going to stop sharing and hand off to him to go ahead and bring us a little bit more of a framework of how innovation policies support the development of these technologies.
Thanks, Addison. I really appreciate your talk, and it was very comprehensive. So that actually makes my job a lot easier. I'm going to share my screen now. Whoops, that's the beginning. Or that's the end. Okay, so thanks again for inviting me to speak. The focus of my talk will be innovation needs and policy options for industrial decarbonization. As Addison mentioned, I'm also on the National Academies Committee for Accelerating Decarbonization of the U.S. Energy System. And we released a report about a month ago that identifies technology and policy needs to achieve net zero by mid-century. So this is a figure from the report that displays, in particular, research, development, and demonstration investment needs for the industrial sector, arranged across 4 key technology pillars. And you see a lot of overlap with some of the technologies that Addison mentioned: carbon capture, use, and storage, low carbon fuels, electrification, and energy efficiency. And it's important to pursue all of these pillars in parallel. This figure also arranges our D&D needs according to time frame. So what we need to do in the 2020s, the 2030s, and the 2040s. And this is meant to encompass the entire set of industrial emissions. So it's inclusive of emissions from process heating. It includes thermal storage and recovery, renewable hydrogen for process heat, also hydrogen as a feedstock for ammonia and for iron reduction, high temperature heat pumps, process heat integration for carbon capture, but also cross-cutting technologies like smart manufacturing and strategic energy management. The International Energy Agency has produced something similar in their sustainable development scenario. And this figure shows the time to early adoption for key industrial technologies. Most of them we need to mature in the mid 2030s, gas DRI with CCUS around 2040. But I should point out that the sustainable development scenario is consistent with 2 degrees of warming and reaches net zero emissions by 2070. So the IEA is now in the process of developing a scenario that is consistent with 1.5 degrees of warming that is designed to achieve net zero global emissions around 2050. And I suspect that this moves up the time frame for these technologies in which these technologies are required to mature. So how do you do that? What's the role of policy at accelerating innovation in industrial decarbonization, in thermal decarbonization? Well, one of the easiest ways that comes to mind is just invest in research, development, and demonstration funding. And that's certainly an important component. I do think it's important that we think more broadly about what innovation is. So this is a quote from the National Academies that it's so beautifully written, I just want to read directly. Over the past decades, the United States has seen precipitous cost declines in 5 key technologies. And in each case, these trends were influenced by similar processes involving both proactive public investment in research, development, and demonstration, and the creation of markets to hasten early adoption and ignite private sector innovation and competition. So the point is we need both the technology push, but also demand pull. We need markets that are pulling these technologies to market. Now, my focus has been mostly on the RD&D side, so that's what I will talk about the most. But I just want to acknowledge that innovation is broader and really works best when we have a complete set of policies working in tandem. The committee did note 2 particular gaps in the US innovation system. First is scale up. How do we scale up technologies from the lab setting to commercial or near commercial scale? This is sometimes called the demonstration gap. And the US has virtually stopped funding demonstration projects after the American Recovery and Reinvestment Act of 2009. The second is commercialization. We're very good at innovating and developing new technologies, and you can look at that through patent rates or publications or even clean tech startups. Less good at turning these investments into commercial products. So I'm going to talk about the RD&D portfolio first. Much of the effort over the past few years has focused on expanding RD&D in industrial technologies, and there's a good reason for that. The industrial sector accounts for 22% of direct US greenhouse gas emissions, but only 6% of DOE's energy RD&D portfolio. Most of it is in clean electricity generation or the grid, a quarter in science and cross-cutting technologies, but a very small chunk at the Advanced Manufacturing Office. That primarily focuses on energy and materials efficiency within manufacturing. So as we scale up RD&D, Congress should target these under-resourced sectors like industrial sector for the largest increases. Now, the good news is Congress is listening, and that's actually what has happened. So there's been broad bipartisan support for an expansion of industrial decarbonization, RD&D. This graph shows funding for the Advanced Manufacturing Office broken down into sub-programs. R&D consortia includes things like the Manufacturing USA Institutes, the Manufacturing Development Center, R&D projects. AMO also provides technical assistance in gray. All 3 sub-programs have grown over the last 5 years. In Energizing America, which is a book that I co-authored last year, we recommended that Congress increase AMO's budget to nearly $900 million in fiscal year 2026. A big change just recently is the Energy Act of 2020, which was passed in December. It provides the first reauthorization of DOE's programs in more than a decade. Now, it does not include reauthorization of the Advanced Manufacturing Office. that was just left out at the end. Congress couldn't get it done. That is something they're looking at this session. But it does include several exciting new provisions for industrial emissions. First is it establishes a new industrial emissions reduction technology program at DOE. This is the green line on the graph. This focuses explicitly on industrial decarbonization. So AMO, as I mentioned, is mostly focused on efficiency. This would broaden that mandate to look at deep decarbonization. Now, we don't yet know how DOE will organize this program and whether it will be, for example, a new sub-program within the Advanced Manufacturing Office or something completely separate. I suspect we'll find out more in the coming days as the budget is rolled out. The second big thing is an expansion of carbon capture and utilization RD&D programs to include manufacturing and industrial facilities. So DOE's existing programs have primarily focused on carbon capture at coal power plants. This is really a welcome addition to look at carbon capture in broader settings at industrial facilities like cement and steel. It also establishes an Industrial Technology Innovation Advisory Committee at the Office of Science and Technology Policy. It creates a technical assistance program for industrial emissions reductions. Now, I should say it creates a technical assistance program, but does not authorize funding. So it's kind of just a shell program. We'll have to see what comes of this. It also calls for a national smart manufacturing plan. Coming soon in the near term are these industrial decarbonization roadmaps. So in the Omnibus Appropriations Act of fiscal year 2020, Congress directed DOE to create these industrial decarbonization roadmaps, building off previous studies such as the, some of you may be familiar with the energy bandwidth studies, which focus mostly on improving energy efficiency of different sectors. So this is a broader focus again on deep decarbonization. DOE hosted several workshops last summer to inform, to solicit information and inform the development of these roadmaps. They should be coming out in the next month or so. My understanding is that they're complete. They're just going under review. But these roadmaps will really inform future research directions at AMO. And you can see they picked 5 key industrial sectors that account for more than half of industrial emissions. This is refining, chemicals and plastics, iron and steel, food products, and cement. And then policy developments to be on the lookout for in this coming legislative session. I've broken it out by R&D, demonstration, and early deployment. First, in R&D, the Department of Energy will have to see how they implement some of the new provisions of the Energy Act. Are they going to establish this new industrial emissions decarbonization program as a cross-cutting program? Will it be housed within AMO? DOE has also joined the Undersecretary for Science with the Undersecretary for Energy to hopefully get better coordination between the DOE Office of Science, which funds basic research, and the Applied Energy offices. Then I'm also interested in this topic of technology targets, which can really help frame and provide direction to an R&D program. The Sunshot targets for solar photovoltaics is a great example. DOE really doesn't have any targets for industrial decarbonization or for thermal heating. So I'm interested in whether DOE should maybe set a $1 per kilogram target for hydrogen production or targets for hydrogen use in thermal process heating. Congress is going to revisit some of these provisions that were left out of the Energy Act, including reauthorization of AMO, but also the Hydrogen Fuel Technologies Office. And there's a big opportunity in hydrogen fuel technologies that is primarily focused on transportation sector applications. But we could perhaps broaden that to industrial applications of hydrogen. And then Congress and the executive branch just this morning released a huge infrastructure package that includes R&D provisions. I can't tell you what's in it because I was preparing for this talk, so this will be the first thing that I look at after we're done here today. In demonstration, again, the infrastructure package, I did see that it includes $15 billion for demonstration projects some of which I suspect will be related to demonstration projects for industrial decarbonization. DOE could do this under its own authority as well, but sometimes Congress may want to explicitly authorize demonstration projects to help DOE scale up its promising technologies. And then in the early deployment stage, I haven't talked much about that, but DOE is already looking at using loan guarantees to accelerate offshore wind. And I'm hopeful that they can apply this to some of these industrial decarbonization options. Congress is continuing to look at incentives for green hydrogen, for blue hydrogen, also looking at deployment programs like a green bank. And then Congress and the executive branch are looking at buy clean or government procurement problems, and also the supporting knowledge infrastructure, the environmental performance declarations, the understanding of embodied carbon in the products that we use that could help inform a buy clean program. So that was a quick overview. I'm just going to leave it there and pass the baton.
Thank you, Colin. Colin?
Yeah, let me try to share my screen as well. Everybody seeing the presentation?
Yep.
Cool. Thank you so much for inviting me here as well. And thank you, Edison, for the wonderful introduction and Colin for the wonderful presentation. My name is Fan. I'm from Columbia University. I'm working as a research associate at the Center on Global Energy Policy with special focus on decarbonization and carbon management for the hard to abate sectors, which includes heavy industry, shipping, aviation, and some other sectors as well. So today I'm going to do a very brief and general introduction about how to decarbonize industrial heat. I will focus on the sources of low carbon heat, the cost today, and most importantly, the policy implications we may derive from the analysis we did. So here is an introduction about the context about how important the industrial heat is and why we should decarbonize it. I believe Edison has already done a wonderful job about doing this brief introduction about how large is the industrial heat sector, or how large generally for the industrial sector as well. So I want to give a very quick introduction. Industrial heat is roughly 10% of global CO2 equivalent emission. That is over 5 gigaton of global annual CO2 equivalent emission. That is larger than all the cars and all the planes combined. So that really going to make a very impactful case in terms of the decarbonization of the global emission profile. So if you believe the sustainable aviation fuel is important, decarbonization of the automobiles with electric vehicles is going to make a very impactful case and also going to be a very big market and opportunity. So does industrial heat. This is really the sector we need to focus on in the future because it's really huge, it's really challenging, lots of opportunities in there as well. So we're going to review what are the sources today that is actually available to provide low carbon heat to replace the old fossil heat. The unfortunate news is that there are not a lot of options because there are a lot of requirements about the heat to be qualified to be used for industrial heating. The first one is a high quality, high temperature. As introduction from Edison introduced, there's a wide range of the temperature requirements. Some of them are relatively low temperature. For example, paper and pulp industry requires a temperature roughly 200 degrees Celsius. Some of the chemical production, such as ammonia, methanol, and some hydrogen production from steam methane reforming will require a temperature from 400 degrees Celsius to 800 degrees Celsius. But some of the heavy industry really requires a super high temperature, higher than 100 and higher than 1,000 degrees Celsius. For steel blast furnace at 1,200. For cement, the clinker kiln is 1,400. For glass and ceramics furnace, that's 1,600 degrees Celsius. So there's really high temperature requirement and really limits a lot of the technical availability for providing this low carbon heat. The heat source that we did analysis on that is suitable provide this low carbon heat and satisfy the requirements are hydrogen, electricity, and biomass. For some of the relatively low temperature requirements, such as chemical production and paper and pulp industry, maybe nuclear heat can be applicated as well. But today, most of the nuclear heat is in the form of steam with roughly 300 degrees Celsius temperature. Hopefully in the future, the fourth generation advanced technology of nuclear reactor can provide a much higher temperature range. But the short message is we don't have a lot of options, and in order to be used as industrial heat supply, you really need to have very high temperature, large volume, and high quality. That is the challenge number one. Challenge number two is really the cost. Even we have those technical challenges solved, we have the equipment available, we have the money we really need to build up the plant, the cost for the heat itself is really a big challenge. We did analysis with a wide range of different options, basically all the options we just mentioned. They're showing a wide range of costs as well, but all of them going to be very, very expensive. We're comparing them with the current baseline when we are using natural gas as our comparison. Today, the typical natural gas price in the United States is roughly $2.5 to $3 per MMBTU. For other countries that requires import of natural gas in the form of LNG, the natural gas price is going to be much more higher, from $6 to $8 per MMBTU. But even for the LNG price, comparing with the LNG price, most of the heat source, the low carbon heat source today is still much more expensive, 2 times, 5 times, or even 10 times more expensive. Just to give people a comparison about what does the $3.5 per MMBTU natural gas price means in terms of other heat source. It means a $0.4 per kilogram of hydrogen price. Well, today's hydrogen production cost is 1.2 to 1.5, and it's not clean hydrogen, it's dirty hydrogen. If it's blue hydrogen, meaning it's fossil plus natural gas, fossil plus CCUS, the hydrogen cost is from roughly $2 or even higher. For green hydrogen from water electrolysis with wind and solar, it's going to be $4 to $8 per kg of hydrogen. So today's hydrogen cost is roughly 5 times to 10 times more expensive than today's natural gas price. So even you have all the technical challenges resolved, the cost for the low carbon heat is still very high. Also, equivalently, that means a 1.2 cents per kilowatt hour electricity price, which is also much lower than today's market price of electricity. So the cost is really the challenge number 2. And the third challenge is really the balance between the different dimensions of providing the low carbon heat options. The 3 dimensions are the carbon footprint, technical feasibility, and the costs. Today, we have some low cost options as we discussed, but they typically have a low technical feasibility. For example, nuclear heat and some electricity heat can provide the low cost options. You need to solve the technical feasibility to make sure that the nuclear steam and electricity can actually be used for industrial processes. Some of them have high technical feasibility, that basically the alternative fuels using biofuel, hydrogen, or solid biomass, but they're very, very expensive. If they're not expensive, typically they have a high carbon footprint, so you are not getting any carbon credit by doing this alternative fuel switching. So the balancing between the 3 dimensions, carbon footprint, technical feasibility, and cost challenges really should be the focus of any innovation and any policy to address this challenge. Here we're going to use an additional example from iron steel industry as a demonstration about how hard it is. As we discussed, most of the options can play a role in decarbonization of iron steel industry. Hydrogen, biomass, electricity, and always there's something you can do with CCUS, although it's not an innovation in terms of low carbon heat, but it's always a second option about CCUS. A lot of them have challenges, either cost challenges or carbon footprint challenges for biomass or technical feasibility for zero carbon electricity to fit into the system. And the biggest challenge of all of them is the decarbonization potential. None of the options we just mentioned can deliver a deep decarbonization alone. Some of them can deliver a decarbonization potential about 60%. So it can resolve 60% of the carbon emission from iron steel industry. Some of them are only 10 or 20%. So if we really want to move to net zero, we need more options. Today's production fleet of iron steel industry using blast furnace is really not capable to move to deep decarbonization and eventually net zero. So we need innovation. For example, molten oxide electrolyzers use electricity only to produce iron steel, or we can use combination approach. So instead of using hydrogen or biomass alone, we can use them together, coupled with CCUS retrofit, so we can deliver a deep decarbonization. And particularly CCUS, although it's not a low carbon heat solution, is proved to be very, very important because it can provide roughly 50% decarbonization potential, capable of doing together with biomass and hydrogen to deliver even deeper decarbonization. And most importantly, it is one of the cheapest options in terms of dollar per ton of CO2. Among all the analysis we did, all the options we analyzed, CCUS is definitely one of the cheapest options to apply directly on the iron steel industry. Other low-cost options, including zero carbon electricity feeding into the system. It's not exactly very cheap. It's still higher than $100 per ton of CO2 carbon abatement cost, but it's moderate compared with other options. The combination options really taking an average between the different options, so it's not that expensive. Today, the green hydrogen is very expensive, non-ideal biomass is very expensive. Finally, we may move on to the policy implications. It's going to be very hard for decarbonization of the whole industrial sector and for low carbon heat as well, but it's very important. Traditionally, we can use a lot of policies to resolve some of the problem and accelerate this transition, but some of the conventional policies have very limited values. For example, we want to do the low cost options first. That means zero carbon electricity or CCS retrofit, but that needs infrastructure support, either transmission line for zero carbon power or CCS pipelines to transport CO2. Those infrastructures simply does not exist today. And that means we need to pay a very high upfront cost to build the infrastructure, and that will take time and that will take money. Very fortunately, we're seeing this infrastructure bill coming today with multiple $1 trillion, and hopefully this particular issue can be addressed in the next few years. Secondly, people talk about the carbon pricing proposals to try to accelerate the transition of this deployment about low carbon technologies. But heavy industry is especially not sensitive to any carbon pricing proposals because heavy industry has a very high abatement cost. As we mentioned before, for example, for iron steel industry, the carbon abatement cost is very likely higher than $100, some of them even higher than $200 per ton of CO2. While the typical carbon pricing proposals have a carbon price from $20 to $60 or $80 per ton of CO2. So paying for the carbon tax is really cheaper than doing any actual abatement by using hydrogen or biomass. So instead of doing actual abatement, the plants and the manufacturers are really going to just pay for the carbon tax or simply shut down the plants and move it to somewhere else. Similarly, if we want to do border tariff to protect the local clean production, the border tariff is also going to be very high, similar to the carbon pricing proposals. As we mentioned for iron steel industry, the existing fleet is not capable to do any deep decarbonization, even with the heat solutions. So we really need to consider an asset replacement strategy to replace the current fleet with some new technologies that is capable of allowing more technologies to bring in low carbon heat or low carbon solutions. This is where the policy can actually help a lot. Government can set up a replacement grant inside the infrastructure bill to pay for such asset replacement so we can accelerate this transition. As Edison and Colin also mentioned, we can do government procurement to make sure that it's a low carbon product to get purchased first, since government is always the largest consumer for this industrial goods. We also need to provide special incentives for the early adopters, since a lot of technology is amateur, it requires a lot of research focus, a lot of deployment, a lot of development. Internationally, we have to accept the fact that most of the industrial production does not exist in US anymore. It exists in China, in European Union, and some other developing countries. So we really need international cooperation to set up international standards and bring in participants from companies from another country, including state-owned enterprises. For example, state-owned enterprises from China or the giant petroleum companies from petrostates. Everybody can do a border tariff to collect some money, but that is hardly ever going to address any actual abatement. But fortunately, heavy industry is a very concentrated area. So most of the production is concentrated in just a handful of countries. For example, for iron steel, only 5 countries, China, India, Japan, United States, and Germany, 5 nations combined is covering 2/3 of global iron steel production. So 5 countries is enough to set up international standards or a timeline for decarbonization of the whole industry, which sounds like a promising future, but also very hard to happen from a geopolitical point of view as well. Similar efforts can happen in parallel with Paris Agreement, G20 meetings to make sure this is part of the agenda, part of the discussion, but none of this is happening today and should happen as soon as possible. Long-termly, we also need an innovation agenda. As we mentioned, we don't have a lot of options today. Hopefully, we can have more options and better options in 10 years or 15 years. Towards the future is a low-carbon future. We discussed about the policy, about assist of the deployment, and also address the cost competitiveness because the low-carbon heat is going to be very, very expensive. And also for decarbonization of the single plant, for each plant, the optimum solution has to be selected locally. There's no universal optimum solution. Depending on your local resources and infrastructure, you may select your own local optimum. Do you have hydrogen supply or biomass supply, or you have CO2 storage capacity? You have to address your own local optimum solution. And also we need to address other considerations. For example, heavy industry hires a lot of people. We need to engage in labor into this conversation. A lot of these things have direct connection with national security. For example, iron steel industry is support of the construction or automobile, which is crucial for national security. And also these industries has pollutions, water pollutions, air pollution, so we also need to engage with health impacts. So there's a lot of things we can do within the industry itself and also with other sectors as well. So this will be a brief introduction. I will stop here. If you're interested in any information, you can go to the website or CGEP from Columbia University, and I will stop here. Thank you.
Thank you, Fan. That was very informative and also nice to see a couple of examples of specific processes. Before I turn to Blaine, a reminder that any questions should be submitted to the Q&A box at the bottom. Thank you to those that have already submitted. We're looking forward to having a good discussion after this. And just so you all know, I have a couple up my sleeve as well. So turning to Blaine now, feel free to take over.
Thank you. So I tell you, going last here is pretty useful because a lot of the heavy lifting has been done. By the same token, my personal reading to-do list has expanded dramatically. I was furiously scribbling down notes and links from all the interesting content being shared. And excuse me while I mess around here with my screen view. So I'm Blaine Collison, I'm the executive director of the Renewable Thermal Collaborative, and I'm going to punch in here from a slightly different perspective on all this, which is, I hope, useful. You know, from a high level here, you know, I guess 2 things. If you're at the outset of your career and you're trying to think about, well, what should I work on that would provide me long-term employment certainty? Working on decarbonizing thermal seems like a pretty safe bet because we are in no danger of resolving this in the next, 10 minutes or even say 15 years, unfortunately. So dig in. It's a huge job. I think we've established here so far. It is a gargantuan challenge, the complications are staggering on any number of levels, and it's urgent, right? I mean, the clock is running, and it's running fast and hard, and the things that need to happen here have to happen, right? So the RTC, as I said, I'm sort of coming from the bottom up, and let me contextualize that. The Renewable Thermal Collaborative is a membership initiative. It's co-convened by the World Wildlife Fund, the Center for Climate and Energy Solutions, and David Gardner and Associates, where I work. So 2 NGOs and a boutique clean energy consulting firm, and we exist because 4 years ago, a group of companies that had been longtime leaders in the voluntary renewable electricity markets in the U.S. Here, which is where I spent the previous big chunk of my career, so I got in a room and said, "So this whole renewables thing has been amazing, right? We've invented PPAs, we've invented virtual PPAs. We're doing stuff. We've gone around our utilities, right? We've figured out how to decarbonize Scope 2. Unbelievable. This has been great, right? Yeah. Oh, this is, wow, who knew?" And then someone said, "But I make stuff. My company makes stuff, and most of our emissions are Scope 1 and thermal. Anybody else have that problem?" "Oh yeah, me too." "Great. Anybody have an answer? Because we've got targets." And dead silence. No one had an answer, and I see my colleagues here above, right? It's really hard. The economics are a bear. And so that group of companies sort of turned to the 3 co-conveners and said, "Look, we got to figure this out. We've got goals, sort of irrespective for a moment of your view on planetary science. We've got big public goals. We've got to get after this stuff, right? We've got to figure out what to do. And by the way, the planet needs it. So let's see if we can't run that collaboration and sort of innovation play that we just ran on electricity again." And so here we are, right? And all of these companies and organizations, and you can see most of these are multinational, if not flat out global. They're running what is in the aggregate an incredibly complicated portfolio of facilities. They have, while we don't have chemicals or iron and steel here yet, the full range of industrial heat requirements is represented in that group, right? They're trying to figure out low, medium, and high temp. They're trying to figure it out across the world, right? Unilever, I think, has 200 and some odd global facilities in 60 different countries. That's a complicated matrix of regulatory frameworks, supply chains, local resources, right? Production. And so this group, along with this group of sponsors or solutions providers, is trying to dig into these issues. And the RTC divides our big chunks of work into sort of technology, and there's a lot to do on technology, markets, and policy, right? There's three big lanes of work. And we talk a little bit about policy here. That's obviously the subject today. What I want to highlight, again, sort of going back to the view from all 3 of my colleagues here, right? Looking at Addison pulled up the projection of emissions, right? And we've got to bend that curve massively, and it's gonna take a minute. What's sort of interesting about these companies is that they all agree on that. They're also all looking to start bending it yesterday, right? I mean, they've got goals. Some of them have goals coming due in the next 5-8 years. they're all looking to get started, and there is a broad recognition that policy is a hugely important lever here, right? Both at the big levels that Colin and Fawn particularly were describing, right? I mean, all kinds of federal resources to be deployed, RD&D agendas, right? I mean, fundamental technology stuff. But there's some other dimensions to policy, right? And I'm just going to tease the fact that the RTC has just put out a policy report. It's available for download on our website. And I mean, here's the high level conclusion is that policy has been dramatically underutilized, right? And I will also share that water is wet, right? But policy has not, we have not had a lot of policy attention on thermal and on decarbonizing thermal and on renewable thermal. And so this report takes 100 pages to really stretch that out and to have a look at some of the policies that do exist in places, particularly in Europe. Some of the policies here that are in place at the federal and the state levels, and then some of what's being proposed, right? And, Colin particularly noted, there's actually a lot going on, right? This is there's a moment here, right, where a lot of attention is focused on the policy possibilities here in Washington. And I'm sure by the end of our call today, Colin will have dug through the new infrastructure bill and can tell us what's in there. I mean, one of the things I would point out about policy, and this is true broadly of the RTC's view on technology also, is that this is very much a yes and kind of conversation and kind of opportunity, right? There is no one single true policy solution here. Just as there's no one single true technology solution, right? We're not just going to electrify our way out of this problem, right? We're not going to put up enough wind turbines and solar panels and just get right. Be lovely, but I mean, it's just not possible for a whole bunch of reasons, and needn't be. And I mean, this is actually part of the complication, right? From a company perspective on doing renewable thermal, right? I mean, from a company perspective, an industrial perspective, figuring out renewable electricity was relatively easy, and none of them would say it was easy. But an electron's an electron, right? It's fungible, and it's a question of getting really good at wind and solar, really, and figuring out storage somewhere along the way. And here we are, right? We're starting to figure out storage. The technology suite on thermal is wider. It's broader. There are questions on scale, right? We're sort of looking for what thermal technologies do scale. Some scale better than others. I talk a lot about renewable natural gas. We are not going to RNG our way out of the thermal problem. Doesn't mean that RNG is not a thing worth doing. And one of the places I tie this back to policy is that it's probably pretty useful to design policy and implement policy that captures a broad array of solutions, right? The policy questions probably aren't simply about doing pick your favorite thing, RNG policy. It's about doing renewable thermal policy or decarbonized heat policy, and creating mechanisms and markets. I want to do a callback on that. That can go and find the opportunities, right? Because the opportunities for Unilever may be different than the opportunities for Stanley Black & Decker. So Colin, you pointed out that one of the things that has been really effective here is the combination of public investment and the creation of markets. Yes, absolutely. If we think about I spent my renewables career on the voluntary market side at EPA and then doing corporate advisory. But the RPSs, the state level RPSs, were incredibly important to building those markets, right? And helping the voluntary market would leverage the compliance market and vice versa. And off we went. And suddenly, we've got we've got a thing, and we've got a vibrant renewables electricity market wherein the state RPSs are, I was going to say, are being left behind. Not true. They are in fact ratcheting up. They are in some places catching up with what's become possible. That's an amazing policy success. And frankly, it's an amazing interaction of policy and market success. So the thing I'll close with, here's what our report says. It says there's lots of stuff that could be done here, and we ought to try to do it all, because the clock is running so fast, right? We've got to have technology, R, D, D, and D, and there might be an extra D in there somewhere. More Ds are generally good here. We've got to have market frameworks, right, where companies can efficiently trade, can find opportunities, participate in projects, bring new capacity to market, trade attributes if that's a part of it. Great. We've got to have technology focus. We've got to have we've got to have some support. We did a policy in webinar last week before at the RTC, and I'll close here. But we had Stanley Black & Decker and Cargill on, and here's what they said. I'm gonna paraphrase a 1 hour webinar into 40 seconds. They said, look, we're in, right? We're committed to this, and we're trying to figure it out. We're looking across our operations for opportunities to do this. We need a little bit of help, right, from policymakers. The cost gap is a serious problem here for us, right? And paying 10x for green hydrogen or whatever. Paying 10x is not the path to job security for a corporate global energy manager, right? That's not the recommendation you get to take twice to the C-suite. So the company is saying we need a little help. We don't need you to government to pay for it all. We're willing to invest. We are here. We are willing. We are looking for things to do here. We need a little help closing this gap, and frankly, bring a lot of help to close the gap. We'll take it. But we're in. We're not saying that we're going to sit around and wait for absolute cost parity. We understand there's an innovation cycle here, right? But we need a little help, and that in the short term, if nothing else, policy that helps to close that gap is critically important, right? That'll help get a whole nother wedge of implementation going, and change happening and decarbonization happening, which feeds on itself. And then, of course, from a broader perspective, we need every bit of policy we can get around this space to open up possibilities from any number of different directions. Sorry, let me stop there before I really start to drift.
Blaine, thank you very much. And I think that a lot of these insights are very important, and I want to go ahead and pull this thread with the panel a little bit. It seems like when you created the Renewable Thermal Collaborative, it's the idea of building off of things that were done in the renewable electricity sector, this idea that people can go out and procure decarbonized electricity for their processes as buyers. However, it seems like there's a challenge here, and this is reflected in some of the comments that are coming in through the questions, is electricity has a dense mesh network across the continent. You can have markets that connect renewable generators with users thousands of miles away, but heat is so much more localized. And it seems like some of the challenges to designing deployment policy here can't be directly ported over, but it's much more focused on these helping to support the building of technology locally, helping individual facilities build. Can you talk a little bit about that? What are the limitations? It seems like that maybe that's just my observation, but we can't take the same policy design from electricity here.
Yeah, that's right. There is certainly some adaptation that would have to happen, right? Because heat is a very physical thing. I mean, let's consider a virtual heat PPA, right? Kind of thing. What's interesting about that as an analog is that if part of the problem here is the marginal pricing, and that is part of the problem, having renewable heat thermal RECs, right, TRECs, and having that kind of virtual market would allow companies that want to help drive the creation of a new, pick it, green hydrogen plant somewhere. It would in fact allow them to participate, right? Now, and to direct capital and investment into a new project, right? That's actually a pretty useful model. Now, we absolutely, for sure, positively have to ultimately decarbonize the heat. It is ultimately it's a physical thing, right? And that's a nice segue to consider the financing element of all this, right? We're gonna the sheer volume of equipment transactions, right, retrofits, replacements, some build outs that's going to have to be papered is a massive economic opportunity, right? And someone's going to have to pay for it, and that's probably a really interesting opportunity both for public incentives, right? The ITC and the PTC were also fabulous examples from the renewables industry, and third-party finance, another fabulous example from the electricity industry, right? We didn't rely on the buyers themselves to put in the capital to develop 300 megawatt wind farms. The private capital markets took care of that. It was the long-term offtake commitment by creditworthy counterparties. That's the thing that the buyers brought to bear and that helped move projects forward. And I think that's a useful analog here.
So one of the things I feel I've learned so far, and turning to you, Fan, is we have roadmaps. We kind of technically know the parts that need to be decarbonized, both in heat and other process emissions. And when we look at what Colin had talked about, both the development of innovation programs that push technology out through R&D, but we also heard from your work that some of the maybe the policies that people on this call might think about, a carbon tax might not be enough to fully incentivize the pull. What are the other things we can do, or how do we, we can create the technologies, but if it seems like the main policies that are on the table right now are not enough to incentivize, what else can we do?
Yeah, so the basic information is that the renewable heat source and low carbon heat source might not be as cheap as today's conventional heat source, such as fossil fuel, forever. So they're just not going to be as cheap as the fossil fuels today. So we need additional policies. One thing we can do is to set up an international decarbonization standard. So no matter where you are, you have to obey the standards. So everyone is producing low carbon products, low carbon steel, low carbon cement. Suppose it's an ideal word, it's not very likely to happen, but that could be one of the targets, to have international cooperation and set up national and international standards to work together. So everybody is paying the same cost. So eventually the cost of the industrial products will be a little bit higher, and the cost will be shared by the stakeholders and the ratepayers, and some of them will by taxpayers as well. But there won't be a competition between the dirty production and the clean production. So that could be one of the options. The second one is short-termly, we can actually do government procurement to address some of these challenges. That we have to set up two standards. First of all is the emission standards. You have to meet the standards. For example, the California Buy Clean Act is requiring your cement or steel to have the carbon intensity below a certain threshold, so you can receive the special payment as a special incentive or subsidies. And the second one is how much subsidies you're actually willing to pay. And that depends on each technology and the company's management and etc. And also there could be some other opportunity. For example, if you exceed the emission, you are paying additional carbon tax. if you're below this, you're receiving subsidies, so you're giving double incentives. There are multiple solutions here, but everything of them going to eventually paid by tax or by ratepayers or by stakeholders. The money has to come from somewhere. So that is the biggest challenge.
That's interesting. And, the one thing that an observation from me on what you're just talking about there, but it kind of seems like policy for heat is more indirect, whereas in electricity, you could directly focus on having standards to decarbonize electricity. Here, it's more about the embedded emissions in the product that is sold, which to some degree is not directly just for decarbonizing heat, but also then has implications across the material supply chains and is therefore just an interesting difference here. And so I don't have a question for anyone there, but I do want to turn to Colin, because we had an early question that came from Muhammad Manzoor, who was asking this question, which is it possible to pursue private sector to fund fundamental research? Or how do we get more funding of R&D? I think it goes back to this question of the history of who's funded innovation and how do we incentivize the industrial player to develop the technologies we need, or is it still going to be developed in universities and commercialized out?
Sure. So right now, the private sector is the largest funder of R&D in the United States. I think it's close to 70% of R&D. The government sector is closer to 30%. And those ratios are flipped from where they were shortly after World War II and the Cold War. The government funded close to 70%, private sector was down to 30%. So the private sector is already doing a lot of R&D. However, their incentive is to reap a profit on that investment. And that tends to focus on very incremental near-term improvements in existing technologies or commercializing near commercial technologies. Now, there may be some private sector funding of, I guess you could call it, fundamental research that is driven by end use applications. If, say, a hydrogen electrolyzer company is looking for a material with very specific properties, they may invest in that basic materials research at an early technical readiness level of TRL 1 or 2, but with the idea that it's fulfilling this particular niche and it has some pathway up to commercialization over a very short period of time. But I think we do tend to rely on government funding more for that early stage R&D. Now, one thing that I think he might be getting at is this idea of, will public funding crowd out private sector funding for R&D? And we do have a history of R&D experience going back to the post-World War II, and we actually find that greater public investment in R&D tends to incentivize greater private sector investment as sort of the tail end partner of that commercialization. So more public R&D leads to more private sector R&D.
Thanks, Colin. There are a couple of questions in here that are technology specific. One question about, solar thermal or locally siting nuclear for heat generation, and then questions about hydrogen. The one thing I would point out is all of the, so there is a lot of opportunity to co-locate and utilize otherwise green sources of, or clean sources of heat. However, the challenges of siting new power plants in general are a challenge. And so there is that opportunity to think about electrification of heat there, but there are so many challenges across not just the innovation of creating new technologies, but also the upper bounds of technologies of heat available from some of these sources. One thing I want to do before the end of this time is to turn back and recognizing we have the opportunity of speaking to the research community that is working on these challenges, but we don't always hear their voices in the policy debate. Or informing policymakers on the technology opportunities and challenges. And I think that one thing I would turn back to our panel here is each of your perspectives about how this community can engage on policy. What can a researcher do to help inform our work, or what's going on Capitol Hill or in London or in Brussels or around the world, in the capitals around the world, trying to develop technology? So I'll first turn, I guess, just in the previous order of how we had started the panel. So I'll start with you, Colin. And I know you're trained as a scientist by background, but have come into policy work. Can you give a little bit of perspective to those that are on this call?
Yeah, so I think I do, because I have this science and technical background. I'm a physicist. I do enjoy diving into the technology to the extent that I can. I think it's important for, first, for some of the landscaping kinds of papers, like the one you did, where we really see a good sense of what are the options for decarbonizing thermal process heating, what are the challenges in terms of cost, what are the targets we need to hit if we're going to look at resistance heating to electrify heating. How does that compare to current cost with natural gas? How does that compare to incumbent technologies, and what are some targets that we should be aiming for? If we're going to look at combustion of hydrogen, how low does the cost of hydrogen need to be? And Fawn, I know you and Julio Freeman have also done these kinds of landscape analyses. So this is very good for policymakers to understand where should we recommend putting R&D dollars. I also think it's important to hear from from industry players. So when there are researchers at the university or at national labs that are collaborating with the industry to address particular practical needs, that amplifies that message even more.
Thanks, Colin. Fawn, do you have anything to add there about how can researchers also act as good citizens on this issue?
Yeah, so basically it's the researcher's job and the professional practitioner's jobs to arise a public awareness. The political issue is really about public issues. So if the population care about decarbonization, the politician and the whole the public entity will care about the decarbonization. And the heavy industry, for example, is really the sector that's public awareness is very, very low. Instead of heavy industry, let's give an example. For example, in EV or electricity, people pay for electricity and pay for buy cars. So EVs and electricities has a high public awareness. They really want to decarbonize these sectors, and it's directly related to their life. But people don't go to the market to buy a ton of cement or buy a ton of steel. So these sectors is really a little bit far from people's awareness. But this part is also very important. It's our job, it's the professional practitioners' jobs, the researchers' job to raise a public awareness saying that this is very important as well, or possibly by the CO2 emission quantity, this is even more important. So that is job number one. So job number two is the decarbonization of this in terms of affecting the final products cost is not as scary. Today, the material cost for a building, for a car, for a bridge is really not that big. So if you double the cost for a steel, for cement, the final cost for a building, for a bridge, for a car, maybe just increase by 1% or 2% or maximally a few percent. So it's not that scary. It's definitely affordable. So the public may be willing to pay for this, but that needs support of the policies and the public awareness. So people don't know about this, and they should be knowing. That is the researchers can really help to as our citizens' duty.
And Blaine, as you sit representing industry that is interested in attacking this problem, are you hearing from researchers enough? Are the technologists coming out of the woodwork, or do you need more people reaching out to these companies and engaging?
Come on, come on in. The water's fine. that's actually a really great question, Addison. One of the things that our members said early is, and I should say, most of the staff that participate in the RTC from the companies are engineers, right? And they're really interested in some of these. Sorry, I'm wrestling with my internet here at the same time. They're really interested in the technologies and the subtleties.
Just seeing you flash in and out, but we can hear you fine.
Great. Sorry for the distraction. What they've said is, hey, look, we don't know what we don't know. We need to know more about what we can do. The interesting thing there, right, is it what I'm describing winds up being the intersection of the highly theoretical or sort of pure researchy kinds of functions, and okay, well, look, that's nice, but I have to go deploy it in a plant, and the plant, we can afford to turn the plant off for 20 minutes every 2 weeks. So you've got some dandy solution, but with let's talk about the realities of deployment, right? There's a really interesting combination of lenses there. I answered a question in the chat about sort of transmitting heat, and one of our RTC companies has a really interesting solution capturing super low cost renewables, curtailed or negative pricing renewables, and using the electricity to efficiently heat a thermal mass to high industrial temperatures, and it becomes dispatchable heat. Does converting one thing to the other make sense? Maybe not. But in fact, they found a really interesting niche here, where because of the way the market works, the electricity resource can actually be transformed into the heat resource, and it seems to pencil and solve some problems. So that's sort of an interesting example of I think the research meets the practical kind of dialogue that can be very, very helpful.
Well, I know that time is short, and if we're on MIT schedule, actually we should be ending right now, 5 minutes to the time. So the last thing I'll end with is, first, again, thanking our panelists for taking the time today to join. Thank you, Asha, for having us. Thank you to Gong. Thank you to the full coordinating committee. But I would leave with one message, which is one thing we recognize from Blaine is researchers should be more engaged with the companies that are trying to do this, the first mover companies, but also you should be more engaged with the broader debate, is informing through telling people what's possible technically, but also acting as we've got a lot to do in 30 years in a lot of ways. Technologies need to be deploying in the next few decades. And so that means not only do we need to be just in our labs working on technology, but we need to be engaged by advocating for action on this front. And I think that, no better voice than the experts who know the daunting nature of this and the need to push. So thank you all for taking the time to join us today. And hopefully you feel inspired to reach out and think a little bit more broadly about how your technology can be deployed in top context. Oh, look, next webinar is our friend Ravi. Very nice.
Thank you, Addison. Thank you to all the panelists. Just a quick reminder, the next session will be a talk by Dr. Ravi Prasher from Lawrence Berkeley on dynamic and tunable thermal storage and transport. Want to again thank the panelists for today, and one last note to also sign up for our mailing list so that you can check out additional events that are coming and get notifications. Thank you all to everyone who came out, and we'll see you all again next time. Thank you.
Thank you.